Hello everybody, and good afternoon. Good to see some audience at least. So the last speaker talked about the domain of high energy physics. I'll be talking about another domain, that is the domain of exotic nuclear physics. I'm Arup Bandyopadhyay from Variable Energy Cyclotron Center, and this is the title of my presentation. So just to introduce, for the completeness sake, what is RIB? RIB is basically rare isotope beams, or radioactivity is a very sensitive word. So earlier it used to be called radioactive ion beam. So when you are accelerating this, the ions shown here by black dots, which are all stable nuclei, those are typically we accelerate in our accelerators like room temperature cyclotron or superconducting cyclotron. For example, take the case of 16 oxygen, 17 oxygen, 18 oxygen. So these are all are stable beam, and these are in the domain of stable beam accelerators. But if someone can accelerate 15 oxygen, 14 oxygen, or 19 oxygen, 20 oxygen, so that we and deliver that as a beam for experiments, that is called rare ion beam or radioactive ion. So why we need them at all? The prime motivation is the study of exotic nuclei, that is the nuclei away from the line of beta stability. Here the beta stability line shown by these black dots. As you can see, only very few nuclei are stable. And then around 3,000 more shown by this yellow zone have been identified, and there are many more in the green zone, and these two extremes are called neutron drift line and the proton drift line. So there are many nuclei which we are not really using them as an accelerator beam for experiments, but they do exist. Now, why we need it? Because if we can accelerate these beams in the yellow zone or in the green zone and deliver it as an accelerated beam, then there will be large number of available beams. So by suitable choice of projectile and exotic species can be studied with a better signal to noise ratio, because then we can optimize the production of the isotope of my choice. Now, the main motivation behind them are, of course, the unusual neutron to proton ratio leading to these surprising properties like nuclear halo, skin, new magic numbers, unusual decay modes. But life is not so simple, because there are few challenges. First of all, when you are going away from the stability line, the production cross-section is very less. The half-lives are also less short. And in general, compared to what you actually want to study, the other species which are closer to the stability line are produced much more. So the signal from them is predominant compared to the signal from your nucleus of interest. Just to brush up the knowledge, this is R is equal to R0 to the power 1/3 law, what is known from our study of the nuclei on and around the stability line. So you can see this is the typical properties. But then it was found by the study of exotic nuclei that many nuclei show this type of behavior or this type of behavior. The dotted line is basically the proton density distribution as a function of the radius, and the solid line is the neutron density distribution as a function of the radius. So you can see the neutron density distribution is extended much beyond, which in here it is almost uniform thickness, it is called neutron skin, whereas here it is the tail, it is called neutron halo. And it is not one or two nuclei, there are many more nuclei, and the whole game started with the experiment from Tanihata et al. In 1985 in Berkeley, where they identified 11 lithium and 11 beryllium showing these properties. It is shown here, 11 lithium here and 11 beryllium here, and this is R is equal to R0 to the power 1/3 law. So you can see the deviation is quite significant. And to just give you some idea of the order of magnitude, the radius of 11 lithium we are talking about is close to the radius of 208 lead. You see the mass number difference, 11 to 208. And this is a part, some portion of the nuclear chart. You can see halo or spin nuclei, 1 neutron halos, 2 neutron halos. There are some cases where you talk about proton halos also. Then the other thing is the magic numbers. So it is well known, we studied in our analysis that we have some numbers 2, 8, 20, 28, 50, 80 to 126. If the neutron number or proton number corresponds to one of these numbers, then the nuclei are found to be much more stable. But then when you go away from the stability line, these numbers like 8 and 20 seem to be weak and they are not magic numbers anymore, whereas numbers like 16 and 34 appears to be show more magicity. And this is very nicely described in this article in Nature. This is the reference. And one of the interesting isotopes is 54 calcium, which is proven to be doubly magic. So you can see this 20 is basically the classical magic number, whereas 34 is the new magic number from the study of exotic nuclei. It has been discovered in Riken Arabia factory in Japan. Then the next thing I will talk about is exotic decay modes. So, for example, proton and 2-proton decay. On the proton grid line, proton unbound nuclei may show finite lifetime due to the Coulomb barrier. So, that gives us the opportunity to allow experimental study of proton unbound states, and these are the 3 examples, but it is not limited to 3. You can see all these blinking dots are basically showing proton radioactivity. This is taken from this reference. It is a very nice review. Any researcher working in this field is worth following. Then that is not the only exotic decay mode. Beta decay of very nuclei away from the stability line, the Q value is so high they can populate in the daughter particle unbound states, resulting in beta-delayed proton, 2-proton, alpha, and neutron emission. In fact, this is one of the spectrum from one of our experiments, which is this reference, where we have studied the beta decay of 24 silicon. Then let us come to the another thing, which is very much connected to this conference, synthesis of nuclei. So the data needed for astrophysics are mass that determines the limits of existence, half-lives, matter distribution, shell closures, excited states, decay modes, and neutron number and proton number cross sections. Actually, all these data are needed for all the nuclei away from the stability line also. Because unless you get that data and put those data in your calculation of the what I should say, for the prediction of the abundance, all this data is necessary. Because unless you get this data, it will be erroneous. So I am giving you one example. Suppose half-life, you can measure half-life of completely stripped nuclei, means nuclei which are not having any electron at all, or you can have a half-life of a uncharged, neutral nuclei. So for example, take the case of rhenium. So half-life has been measured for 75 plus, means all the electrons have been stripped off, and here it is neutral. So here in this case it is a 42 million years half-life, and here it is 33 years. So you can see the order of magnitude difference. So depending on that, the prediction of the nuclear abundance will be differ very significantly. This is measurement done at GSI Germany. So RIB facilities are needed for studying this type of properties also, and there is a need for systematic study of a large number of nuclei for the refinement and better predictability of nuclear models. So each such measurement on any nuclei will provide new data, and that will refine our existing nuclear models. So it is a continuous process. Then exotic nuclei also play a very crucial role in explosive nucleosynthesis. This is a very familiar nuclear chart. So the fusion reaction stops at iron. This is the red line. Slow capture process or S process is possible up to 209 bismuth. Beyond bismuth, it is R process shown by this zigzag line. And so all these processes, and you can see this blue line totally in the away from the stability line. This red line is this violet line is also like that. So the exotic nuclei study will give you all this information, and it is very nicely said by Nobel laureate Fowler of B2H FH frame. It It is in my view that the continued development and application of RIB techniques could bring the most exciting results in laboratory astrophysics in the next decade. Now the examples I have been giving so far are all related to the nuclear physics. It doesn't mean that the RIB is needed only for nuclear physics. It is important for other realms of physics also. Just to give you one example, there's a very important study in the material science, formation and propagation of lattice defects. It is very much connected to our nuclear program. When you develop some nuclear material, by neutron bombardment, whether some deformation will be introduced or not, and how with time that deformation will propagate. This is a very important study. Otherwise, you cannot put just any arbitrary material within a nuclear reactor. So earlier or historically, the way to study this is by this Rutherford backscattering technique shown on the top side. It is called ion beam channeling. But then using RIB, you can do another interesting study. So you basically impinge with RI beams, and then you study the emission channeling, that is positron, electron, or alpha spectroscopy. Now the efficiency of these nuclear techniques is very, very high. So it gives you two advantages. First, required implantation dose of the RIBs is significantly lower. So radiation damage during channeling analysis is very negligible. You should not destroy the sample what you are trying to study. And sensitivity is almost 5 orders of magnitude higher. From another realm of study, radioisotope theory, a radionuclide is delivered to a tumor site using a biological active molecule which decays via beta or alpha. Now, the main goal is that it should produce minimal damage to the healthy cells compared to the other nearby cancerous cells. Now, for example, for thyroid cancer, this is the isotope. There are isotopes which are used for bile duct cancer, liver cancer. For prostate cancer, ultimately it can lead to bone metastasis, and the isotope which is used actually 223 radium, and the commercial name is Zofino. Then for digestive tracts of stomach, pancreas, intestine, etc., the typical isotope is 177 lutetium. The commercial name is Lutathera. So using RIB, these are produced as such also, but using RIB, one can produce such nuclei with a very high specific activity, as it will be carrier-free or no carrier-added form, that we can fine-tune using suitable target projectile combination and a very clean separation which is available in any type of RIB facility. And this study will also has the potential of finding new radioisotopes for different other types of treatment. So, to summarize, RIBs offer excellent research opportunities in various fields of accelerator field-based research. Now, there are different countries, different laboratories are doing research on RIBs, or either in the development of RIBs or research with RIBs. So this is a very nice report from the US Rare Isotope Science Assessment Committee. So I am showing a part of those facilities which are highlighted here. RIB Patrician is one of the most powerful facilities today. Then this Leuven, Belgium, this is historically very important because they are the people who first accelerated RIBs. Then you have here at GSI, you have ISORD at CERN. ISORD at CERN, as you can say, is for the first ISORD type of RIB facility, and it is something like they have produced too many isotopes and for the study of exotic nuclei, and a lot of research is going on in their facility. And also it is interesting to note that our RIB facility has also been mentioned in this chapter. Some other facilities, Spiral 2 at Canil, Isaac 1 and Isaac 2, which is also known as Ariel, RIA, which is also known as FRIP now. So these are all world-class facilities. So I'm just trying to convince you this is a very important field of research. I have shown you first a few of the options of RIB research, and also I have shown you. No, I have just said the heading. There are many facilities. So that this, no, it is written selected list of rare isotopes. Yeah. I'm not writing, it's I'm taking just the tables from the.
It's not this table is wrong.
Yeah.
Started today. Go ahead.
So, with this introduction about the Array beams and array beam in physics, I'll now concentrate what we have been doing in VCC. So, the next part will cover these three aspects: exotic nuclei research in VCC, rare beam facility in VCC, advanced measurement facility for unstable and rare isotope beams called ONURI. So, you can think it in this way: this is the past, this is the present, and this is the future. So we started around 1988. This is a facility which uses helium jet gas transport system. The idea is, in the accelerator cave, you use a suitable target to produce exotic nuclei, transfer the reaction products to a low background site by using this technique. The technique is by the differential pumping of a carrier gas. It is shown here, helium, with some added impurity. So this helps you to take it to the low background site, because otherwise you won't be able to see the signal from very low production cross-section nuclei, and you have your detector set up, etc. Using this type of facility, some interesting experiments was done. For example, identification of a new 3-second isomer in holmium in this reference, where 29 to 40 maybe alpha particle was used. Then this is another experiment using 60 mpb alpha particle beam from cyclotron, where 2 new levels were established, 4 levels from earlier in-beam study was confirmed, 8 new gamma transitions were observed. This is, another interesting study. As I said in the description of exotic decay modes, that exotic nuclei show very high Q value. So if you want to measure those high Q value reactions or beta decays, you need very large volume beta detectors, which are not available as such out of the shelf. So you have to develop very large plastic scintillation detectors, and you have to develop a methodology to find that how to use that detector and exactly accurately find the beta decay endpoint. So we have been done these tasks. So here you can see this is a spectra for the standard source, singles, gated, and strontium standard source. And for this particular nucleus, we measured the beta endpoint 98 rhodium, and this was the beta endpoint energy. So it was, the earlier measurement was erroneous by about 600 keV, and this is the reference for that. Then gradually what we realized, as I said, for helium jet technique, you can take the reaction products to a low background site, but still all the reaction products are transported. You do not have any separation. So if you want to study very low cross section, or some product which has been produced from fission, where a lot of reaction channels open up, you need some stage of separation. So the next very methodical stage was development of helium jet coupled isol facility. This is a picture of that. This has been developed around 2006. These are the spectra, and here you can see the separation between two nuclei. These are the parameters of the system: resolving power 866, dispersion is this, and it is equipped with hollow cathode ion source, operating surface ionization, and plasma mode. Now, let us see how array beams can be produced. So, normally in an accelerator, you have a source or a feed material. Suppose you want to accelerate oxygen, you will have oxygen cylinder. You have a suitable ion source, so oxygen will be converted to oxygen ion. There will be different charge states, so you need a charge state separator, followed by ion accelerator. That can be anything, that can be a pelletron, that can be a cyclotron or linac, anything. So this is basically the building blocks of a primary accelerator. So in the same analogy, the RI beams also, we should have a RIB feed material, suitable ion source, blah blah blah. But that is not possible because there is no RIB feed material available. Because RIB feed material decay as per their half-life. So if you want to study low short-lived products, it is impossible to get this RIB feed material. So the way out is like this. You have a primary beam accelerator, you take the beam from this accelerator, use the primary beam target, the reaction products which are produced, that is acting as a feed material, and that you are feeding to a suitable ion source, followed by this same sequence. So this is what an ideal post-accelerator type of RIB facility looks like. So you have a source material, suitable ion source, isotope separator, ion accelerator. So this is the primary accelerator, and this is the secondary accelerator. Now in this method, the energy of the beam is very low. So generally you have a post-accelerators also for this type of facility. Now in the projectile fragment separator, almost in a similar way, let us see how it differs from the ideal post-accelerator type of RIB facility. Here, the first difference is, as the name implies, the reaction by which you will be producing RIB is projectile fragmentation reaction. And generally, the primary accelerator is around 300 MeV per nucleon heavy ions. Here, you do not need suitable ion source because the projectile fragments themselves are already ionized state. So you do not need any ion source. And the isotope separator in this case is called a projectile fragment separator. And then you do not need any ion accelerators also, because here the projectile fragments are almost having the same energy. So these post accelerators are also not required. So projectile fragment separator in this way, it was slightly different. These are the two ways of doing RIBs, of producing RIBs. So we started thinking what will be the optimum route for us in VCC to produce RIBs, or what type of facility we should think about. And the time I am talking about, at that time we had the expertise of implementing room temperature cyclotron and operating experience for many years. Superconducting cyclotron was being built at that point of time. So with that experience, then the question of the time scale which will be required for a isol post-accelerator type of facility or projectile fragment separator type of facility, we thought it would be appropriate to develop an isol post-accelerator type of RIB facility, and we went to that direction. This is a schematic diagram of the radioactive facility in Bidhanganur campus of the ECC. So we take the beam from K130 cyclotron. We use either thin target or multiple thin targets. Charge treated is nothing but ion sources. After that, you will have many exotic nuclei, but you want to select one of them to be used as a beam.